And that's pretty much what we have to learn for beta sheets. The interesting thing is that there is remarkably little diversity, as I said when we started to study them. Although when you look at them in the PDB, you're going to think that they're disordered and diverse. But draw those schematic cartoons, in particular if somebody gives you a structure, and you will realize that they're more common than you might think. In fact, if you just pick a few here beta strands, 4, there are not that many ways you can organize them. Again, it's just a matter of mathematics and permutations, right? But of all these ways, it's pretty much only the underlined we see in nature. Again, there are some of these are rare and might be occur in a handful of structures, but in the tens of thousands of structures we know in practice, that one, a simple beta meander, is very common. And these two are super common. Do you see what pattern they share? That's right, the Greek key loops at the top. Doesn't mean that the other ones will never occur, but they're so rare that when it comes to predicting protein structure, there are quite a few programs and bioinformaticians, they only try to predict structures, combinations of beta strands that have already been observed in nature. Because the likelihood that a new protein, whose structure we have not determined yet, will contain a combination that has never seen before is the first approximation 0. So again, there are very good regular rules and it's rare that we break them. But the difference between physics and biology is that in biology there are exceptions to these rules. Let me show you one. Pepsine. What is wrong with this structure, or what appears wrong? Do you see that green loop over here and the yellow one? Imagine taking the red and the blue, the red and the purple ends of this protein and just pulling them. What would happen? You might need to think about that a minute. But what's happened over here is that we actually have a knot. So the protein looks completely normal until you get towards the yellow part here. The yellow part literally goes inside this long green loop and up the red one. So if I tried to pull this, I would literally form a physical knot at the end. It would not be a stretched out chain. That would you would never see that in a protein. And if I created a structure and I or one of my students created a model like that, my colleague would likely say, Eric, you made a mistake. There should not be a knot in that loop. And again, he would likely be right. So when you see something like this, there is a reason for it. I haven't told you what protein this is. This is a protein called pepsine that occurs in your stomach tract. What happens in the stomach? The stomach is a very nasty environment. You might have a pH down to 1 or so. And the whole idea, the stomach is a place where we're breaking down proteins. If you want a protein that's an enzyme that should work there, it had better be super stable or this enzyme would break down too, right? When you create something like a knot, you likely create a fold that is extremely strong and makes it difficult for other enzymes to unfold this protein, which is again likely the reason why this has evolved. So you might argue that there are exceptions and they're not interesting because they're exceptions. I would actually argue the opposite. The exceptions are interesting because they tell us something about the rules. And in this particular case, it's a protein that had to survive at exceptionally low pH, which is of course not needed for other proteins. But this one does need it.